Hi there, Year 12. I want to run through 19C2 with you. This seems to be working out, well, hopefully it's working out well for you. So in 19C2, they look further at displacement and velocity functions. So displacement was introduced in C1. So displacement can be either positive or negative. It's a vector quantity. Hopefully you remember that. If it's a positive displacement, then that means what? It means the position is to the right of the origin or above or up, above the ground level or whatever. If it's a negative displacement, it means it's to the left of the origin or down below. S is the symbol we use for displacement. So S is displacement here. To get our displacement, we want the integral of velocity. So we talked a bit about that in 9C1. So if we're integrating and we want displacement, we want to get the change of position. So displacement is different to distance travel. Distance travel is how far the particle or whoever it is moving has gone overall. Displacement is just simply saying what's the change of position. So what's the final position minus the initial position. So we can get that simply by integrating a velocity function from T1 to T2. What it does in between T1 and T2, you've got no idea. It could have just gone straight from the first position to the final position. It could have gone all the way to Central Station and back to get to the second position. You have no idea what happened in between. It's just simply overall what's the change in position. Distance travel is always positive. It's a scalar quantity. So we don't have a positive or a negative distance travelled, but we can have a positive or negative displacement. To calculate your distance travelled, remember, you need to find the points where the particle stops and turns around, then work out each section separately, or you can take the integral of the absolute value. So we can highlight those important points for you. So if you want an integral of the absolute value, nice straight line. Oh, there we go. Otherwise, you're going to find out where the particle stops and turns around and work out each section separately. There we go. Do you need to know the starting position? Do you need to know where the particle is initially to find either the distance travelled or the displacement? What do you think? Hopefully you gave the answer no. So it doesn't matter where the particle is initially, if you're trying to just find out how far it goes from then, or where's the final position. Total distance travelled, remember, is T1 from T2, but you're taking the absolute value. So that's those absolute value signs that allow that. So displacement's a vector quantity and describes the overall change in position. Velocity is also a vector quantity. Remember, a positive velocity means what? Hopefully you are thinking positive velocity means it is travelling to the right, which is our positive direction. Oh, I can't spell it. Sorry. So it's either travelling in a positive direction or which is usually to the right. If it's negative velocity, it means it's moving to the left or down, whichever the negative direction is. So here we've got an example. I've drawn in a function, looks a little bit like a sine curve. Velocity versus time. Here's our time 1, time 2. Whereabouts does it have the greatest velocity? Have a look at your graph. Where do you think it's the greatest? Hopefully you've gone right. Here's the highest velocity. So at time 2, it has the greatest velocity. What about the greatest speed? Do you think the greatest speed is at T1 or T2? If we think about it, speed is just simply saying how far something is going. It's irrespective direction. It's a scalar quantity. So the greatest speed is actually at T1 And that's because it's the furthest distance from the x-axis. So this might be negative whatever, but it's more negative than, like, it's compared to this one, it's positive something. So let's say that's positive 5, this is positive 8. The speed is 8 kilometres per hour, or whatever the units. Here the speed is only 5. So whichever one is furthest from the, pick a different colour, whichever's furthest from the x-axis, that's your greatest speed. All right, so let's now, missed the bit down the bottom. Turn off phones in class. Velocity and acceleration. So velocity is, hold on, all right, so velocity is the integral of acceleration. So remember we looked at acceleration as the rate of change of velocity, so this is the reverse. So if we want to get displacement and we want the rate of change of displacement, then we get velocity. If we differentiate the rate of change of velocity, we then get acceleration. So the reverse is true. When we integrate acceleration, we're getting velocity. When we integrate velocity, we get displacement. Note we need specific values to substitute in to determine that constant of integration. So every time we integrate, we get a constant, get another constant. So you need some initial or some values to put in to calculate the constant value. All right, so let's look at this example that we were doing earlier. This is the one we looked at in 19C.1. Our velocity function, t squared minus 5t plus 4. So this is our velocity, so positive velocity. It then stopped, moving in the positive direction, stopped, started moving in the negative direction, stopped, turned around, went positive again. So we talked about that in 9C1. What's happening about acceleration? So remember acceleration, that's we differentiate to get from velocity to acceleration. So when we differentiate here, we're thinking, what's the slope of the curve? This is all a negative slope. So we have a negative acceleration. Then here is our minimum velocity, and it's a turning point. So that's our acceleration equal to 0. Then over here, we have our positive velocity, and that's represented our positive slope going up here. So the positive value for the acceleration is saying that we have an increase in velocity. In here, the area under here is going to be telling us about the velocity of the function. The area under here is telling us about the velocity. Note this area is negative, and so our velocity is negative. All right. And over here, positive gradient representing the positive area here. All right, so in this example here, the particle P moves in a straight line with this velocity. This is out of your textbook. You're asked to answer this without a calculator. So how far does the particle travel in the first 4 seconds of motion? If it's saying how far does it travel, it's talking about distance travelled. Whereas in part B it says find the displacement of P after 4 seconds. That's about is displacement, it's not distance travelled. No calculator, I still like to go to sketch a graph. In the textbook it goes through a sign diagram, but I like to think I can factorise that, I can do a quick sketch. So you should be able to sketch this graph up without your calculator. You could do a sign diagram or a motion diagram. So if I want the distance travelled, then remember that's the scalar quantity. I want the absolute value of the velocity function. So you could do that. Then if you think, well, that's too hard for me to do without my calculator, then break it into those sections. Work out where it stopped. So it stopped at 1 and it stopped at 2. Then work out the area under the curve from 0 to 1. So that's this area here. Can I colour it in? Let me try and do some colouring. Oh, this area. Okay. I then want to get the negative part of this bit, all right, because that's below the axis, so I need to take the negative of it. That's the green part. I need the negative of that. And then this last part, I'm going to take the positive of it, so I add that bit on. There we go. Can you see the negative sign? All right, so you can just break it into bits. Whereas in part B, it's just simply saying, what's the displacement after 4 seconds? Then you're just simply going to integrate it from 0 to 4 to see the change of displacement. And it looks like it's going to be positive because the positive areas are bigger than this negative area. So it's moved further to the right or up overall, but you'll need to do that calculation to find that out. In the textbook, let me just quickly put up what they did. They did the same sort of thing, except they factorized it. Then they did their sign diagram. They worked out it changes directions at these times. So what they've done is they've integrated the function to get this and then found out the different positions and included the c value. Then using the sign diagram, they've worked out the distance travelled between each of these. So now, to me, this is quite a complicated way. They've found the different positions at 1, 0, 1, 2, and 4, and then subtracted them. So you can see this first bit here is how far has it travelled from s of 1 at 1 second. So it's c plus 5, 6 minus c. So between 0 and 1 second, between 1 and 2 seconds, between 2 and 4. So it's, I think, quite complicated. The c's all cancel out. Overall, the distance travelled is 5 2/3. So that, to me, is a more complicated way of dealing with it. The change of the displacement, the final position minus the initial, they've just simply got s of 4 and minus s of 0 and subtracted them. So overall, there's a change of 5 1/3 metres to the right. Anyway, so that's the way they did that. As I said, I think it's a little bit complicated. You don't need to include all the C's. So I just wanted to quickly run through this question 8 in the section. Here we've got a particle at the origin, is initially at the origin and is stationary, accelerates according to this function. Find the velocity function for the particle. So at t equals 0, it is at the origin and stationary. So that means s of 0 is 0 and v of 0 is 0. To get our velocity function, we want to integrate this. So we're taking the integral of the acceleration function, integral of that, minus 1 over t plus 1 all squared. Remember, this is just like a polynomial function. I've written as t plus 1 to the minus 2. All right. And the minus out the front here, I've taken outside the integral sign just to get it out of the road. So our rule says add 1 to the index and then divide by the new index. So we've got now to the minus 1 here, and we're dividing by minus 1. And remember, if it's f of ax plus b, we then want to multiply by 1 on a. So the a in this case is 1, the coefficient of t, and we're dividing by 1. So we've got 1 over 1. There's our new index, minus 1 from the minus 1. That's our minus from the front of our integral, plus c. Now we want to get a value for c. We can now substitute in our conditions. Sorry, I've cancelled all the minuses here. So at t equals 0, our velocity is also equal to 0. Substitute in 0, and we come down and find that c is equal to minus 1. So here's our velocity function. Now in part B, we're trying to find the displacement function. So we do exactly the same thing again. We want the integral of our velocity function. So we've now found that that is equal to 1 over t plus 1 minus 1, integral dt. Integrating that, we find out that, remember that the integral of 1 over a function is the log, natural log. So we've got the natural log, absolute value of t plus 1. Integral of minus 1 is minus t, plus c again. There's our plus c. Now we can put in our initial conditions. We know at time 0 our displacement is 0. So 0 is equal to ln of 1 because t is equal to 0, minus 0 down here, plus c. And we remember all our log rules, of course. C is equal to 0 because log of 1 is 0. So our displacement function is the natural log of t plus 1, absolute value, minus t. All right, so use your initial conditions. Then back in part C, describe the motion of the particle at the time t equal to 2. At t equal to 2, our velocity, let's put a comma in there, our velocity is equal to minus 2/3. So what does that mean? The particle is moving in the negative direction with a speed of 2/3 meters per second. Anyway, so there's an example, one of the questions we've worked through. Hopefully this makes sense, and looking forward to seeing you in class again. Thanks for listening. Bye for now.